This video presents our work on learning extended body schemas from visual key points for object manipulation. In this work, we present an approach to learn visual key points by merging visual and proprioceptive information. We also show how we can use the visual key points to learn an extended kinematic chain that includes an object in the manipulator's hand. We extend the self-supervised visual key point detector by Meier et al. To also include proprioceptive information. Specifically, we add a component that includes proprioceptive information during key point detector training. The current joint pose of the manipulator is used in a forward kinematics call that projects the end effector position directly into image space. The projection is used to create a kinematic feature map that spatially biases the key points to be around the end effector. The current image is used to create a visual feature map. The kinematic and the visual feature maps are then combined to create a joint feature map that is used to eventually recover the key point locations on the image. We now compare the detector presented by Meier et al. To our detector that leverages proprioceptive information during training. We can see that our approach is the only one that reliably places the key points on the object. We use our key point detector to learn the extended kinematic chain of the robot. For this, we use RGB image data and the detected key points detected by our key point detector, together with the depth image, to learn an extended kinematic chain where we define virtual joints that represent the object in the manipulator's hand. We learn the translation parameters of the virtual joints, formulating a loss that uses the visual key points as a regression objective. We are able to learn the parameters of the virtual joints from a few frames, such that the resulting extended kinematic chain can be used for a manipulation task. The red circles in the image on the right represent the projection of the virtual joints in the image learned from few frames. We now show experiments for a manipulation task where the actions were optimized using the extended kinematic chain, where we compute a loss function that measures the distance in pixel space of the projected virtual joint positions and the goal positions for the trajectory, and optimizes the actions by taking the gradient of this loss function. We can see that for both initial configurations of the robot, the bottle was successfully placed, meaning that our approach successfully learns how to integrate the object into the kinematic chain of the robot.